Yeah, everyone, this is a video demonstration for my new blog post on how to bootstrap a Kubernetes cluster on your laptop using Terraform, Ansible, KVM virtualization, and Kubeadm. And this is an extension of my previous post where we used Ansible and Terraform to provision and configure self-hosted virtual machines with custom disk images on your Linux system. So I've gone ahead and I've extended Terraform now to provision 3 virtual machines. One will be the control plane on the Kubernetes cluster, and the other two will access the worker nodes. And the Ansible playbook now takes care of setting up the environment on each machine, ready for Kubeadm initialization and setting up the cluster, right? So if we take a look at the Terraform now, you can see we now loop over the machines we want to provision, and those are defined in the variables file. So we now have them defined here. They have the same configuration, but it's just a test environment, right? So we're now going to loop over each virtual machine and provision up the 3 that we desire. And if we check the Ansible, you see we now do quite a lot of work to configure the environment ready for Kubeadm. We need to install the containerd runtime and the Kubernetes command line tools like the kubelet, the Kubeadm, and kubecontrol. And we need to set some kernel parameters, disable swaps, and configure the host file on each machine to be able to find one another, right? So it's quite a lot of work to do. It's nice to delegate it to Ansible, especially since you have to do it 3 times, or at least 3 times for each machine you want to put into your Kubernetes cluster, right? So once you've got all this up and running, as I say, it's quite straightforward. You just come over and run Terraform apply. So that just took a couple of minutes to finish provisioning all the machines on my machine, and you can see now we have the IP addresses of the nodes output here. We can also check in the Ansible inventory that's been updated. So Ansible now will be able to find the machines as well by these host names. In fact, if we are to run the Ansible playbook, you will see that the Ansible is able to successfully go through the playbook we've defined and configure the environment on each node ready for cluster initialization. So now that everything has been configured, we're ready to move on to step 2, which is initializing the control plane. So we simply have to SSH into the master node. And run this command. Sudo kubeadm init, of course, make sure to run as root, and we're passing in a pod network CIDR here because this is what the flannel CNI requires, which we're going to install afterwards, and we'll specify a DNS name for our control plane endpoint. So the output shows us that the control plane was initialized successfully, and it tells us to run these commands in order to start using cluster as non-root user. So we'll go ahead and do that. And the next thing we should do is deploy a pod network to the cluster, which we're going to use Flannel for. Since Kubernetes delegates pod networking to CNI plugins, or container network interfaces, which are responsible for assigning IP addresses to pods and enabling cross-node communication. So out of the box, that will not work unless we install a plugin. So we're going to use Flannel, which is probably the easiest one to get up and going with. It just works out of the box. I think it doesn't have as much functionality as somebody else. And after you install Flannel, you can check that the core DNS pods are up and running. But they'll just take a minute to get ready once that's been installed. Okay, so it looks like the networking has been configured correctly. So the next step is to join the worker nodes. I'll open up a terminal for this. And we're just going to SSH onto each worker. and go ahead and run the kubectl join command that was output when we initialized the cluster. Make sure to not use this one to join. This is to join another node as a control plane, which is a more involved process because you have to copy the certificate authorities and the service account keys. We just want to join the node as a worker node, so that would be this command. Of course, you need to run this as root. And simply repeat the process on the next worker node. And once you've done that, you can check the status of the nodes from the control plane. And it takes about a minute for the nodes to transition to being ready. So at this point, with the nodes joined and ready, we essentially have a functioning cluster. So we're ready to deploy a test workload. And we'll just use nginx for that. So we'll create a deployment quickly, passing in the nginx image. That's image equals nginx. And we can check the status of the pods, and we can also check which worker node it got assigned to. It looks like it got assigned to worker node 2 arbitrarily. So let's go ahead and expose this deployment using a node port, and then we can access it from our host machine. Okay, it looks like it's running on port 30557 now. So if we come back over to our host machine, and we curl worker node 2, we pass in this node port. You see we get the correct response for nginx. And just to demonstrate, you can also pass in the IP address of worker node 1, or the control plane even, because the node port will take care of the networking and redirection. So at this point, we already have quite a functional cluster, but if you'd like to go further, there are a couple more extensions we can make. By default, local Kubernetes clusters don't have any support for persistent storage, and this problem is solved by Ranch's local path provisioner project, which enables dynamic provisioning using the node local disks. So it's quite easy to install this. We simply apply the latest release from the Ranch project on the control plane, and just patch the storage class to make it a default storage provisioner, and then verify it's worked. And then we can do a little test just to demonstrate the storage works, which can use a busybox pod to write to this data location. We can check the persistent volumes. It bound successfully. And if we cat out the contents of the data directory. You can see that what we wanted to input has been written successfully. Right, so all that we're missing now is support for a load balancer resource, because this is delegated to the cloud providers. However, this is a problem that's solved by the Metal LB project, which is the de facto standard for a bare metal load balancing solution for Kubernetes. So this will allow us to assign a real IP address from a pool on a local network, allowing us to access resources on the cluster from the host without having to specify a port number. And again, easy to install. Simply apply the latest YAML. Verify that the pods in the Metal LB system are all running correctly. While that's working, I'll just write the configuration file to tell it to which IP addresses to assign from. And we simply apply the configuration. Okay, now we're ready to expose our deployment again, but this time we're going to use a load balancer resource. So we'll just say kubectl expose deployment, nginx, port equals 80, type equals load balancer, name equals nginx load balancer. And you can see it's now provisioned an external IP address, which we should be able to access directly from the host machine. Yeah, and as you can see, that works perfectly. So at this point, we now have a self-hosted Kubernetes cluster that also supports persistent storage and load balancing running on your laptop. And everything's provisioned through infrastructure as code. So it is very easy to tear down and re-provision as much as you would like for ephemeral testing. If you'd like to take this project further, you could look into a high availability setup maybe with at least 3 control planes, and you would set up HA proxy to direct traffic between them. Since we're finished with the lab now, I'll just demonstrate how easy the teardown process is. So just exit from whatever machine you're on and return to the Terraform directory and simply run Terraform destroy. Yeah, and in a few seconds, you can see all of the resources were destroyed. And if we check the state of virtualization on the system, everything is now back to baseline. So very easy to bootstrap and tear down any kinds of testing workloads you would like to do. Well, thank you for watching this video, and good luck with your Kubernetes clusters.